All right, did anybody not get the email? Okay, the file should be dropped in here. I don't think it'll need to be activated, but all of these components, when you download them from the web, sometimes have an extra button here on the properties menu for the file that says unblock. If yours does, go ahead and click that. If you have that dropped in there, you can close this, close Grasshopper, and then you just have to do unload. So Grasshopper unload plugin, and then restart the plugin, and now under the extra menu you should have the hoopsnake component. Now how are we doing? Anybody not have it now? Okay. Alright, so today we're going to start off where we were a couple weeks ago, but we'll kind of start from scratch. So let me going to start with a fresh Rhino instance. Again, we're just going to work on the top plane, so I'm going to double click, maximize that view. Today, just to kind of give everybody the same scale of working on, let's just do a rectangle. I did the rectangle box here. As for first corner, I'm going to just say 0, 0 with the keyboard, and let's set it at 20, 20. Okay. Okay. So now this is just kind of a rough start point. You'd have to work exactly in this box, but this is just to give us similar scale as we work. We're going to do 3 curves. Use a control point curve here, which you can also get to here, but this guy, and just kind of give, these are the C-shaped curves that we did last time, where they're roughly starting and stopping about 11 and finishing at 1, and you hit enter to exit once you've got your final curve. And just do 3. They don't have to be completely inside or outside, but just roughly in this ballpark. Okay, if you're missing this bar, I think the way that it pops is sorry, I just had to turn this on and now I can't remember. Sidebar. Nope. The other place that this is, because this is the kind of catch everything, there might be also, no, it doesn't look like that. No. There we go. This is what I was looking for. Okay, so the next thing we want to do is change, once we have our three curves, we're going to set the elevations of these. So I'm going to just do Control Tab and toggle to through the view states to perspective. Now I should be able to rotate around. I'm going to pick one of these guys, and I have my manipulator here, that's the gumball. If yours doesn't show up with the three colored axis, then click down here to toggle it back on. And go ahead and let's move this up one level. Actually, let's move then we can set the distance.
You just click on the blue arrow and type in.
Ah, sweet. Okay, let's do that. Thank you, Steve. All right, we're gonna do, let's see, what are we at? 20, so let's do 20 for one of them and 10 for another one. Okay, so we're going to import these curves and loft through them so we start to have our working surface for today. Params, curves, that's the tab that'll let us store curves in the model. I'm going to put 3 of these, one for each. And the way you connect those to the curves in the model, right click, set one curve, and select it in the model. And just know that you have to select them in the way where you know the order. You can go top down or bottom up, but you have to do, at least so you know the order when you tell it to do the loft, that you can do it in the right sequence. I did curve under the params tab. So params and then the curve parameter. So this one's just the container. That's one way to start, but now I'm feeling it's a little less parametric than we could do. So let's go back into Rhino and reverse this. Double click and move it back down -20. Oh, I guess that one was 10. Move this back down 20. And that way we can connect that to a slider. We'll do the move in Grasshopper and then have a little more flexibility later. So I'm going to go ahead and bring down 2 moves. So that's, you can double click, type in move, translate an object along a vector. That's what we want to do. So I do still have my order. These are the order, so I'm going to leave the first one on the ground. I'll move this one. By default, this is set to move it up 10. I'm going to copy paste, drag this one over. Okay, so the 2 inputs here, geometry to move, that's inheriting from our curve. And if I mouse over the T, that's a translation vector. You can see there it's the direction and the magnitude of the transfer. It's moving 0 in the X, 0 in the Y, up. 10 in the z-axis. So we need to replace that with something of our own device. Let's go to Vector, and under the Vector tab, grab a unit z vector. Make a little space for this. Alright, so by default, this one comes in and moves it up magnitude of 1. Copy, paste, and we'll wire them. So they're both now moving to 1. And the slider, I'll show you again the notation for the shortcut for making that. So if you double click on the canvas, we want to have, let's say, minimum of 1, less than 10, less than 20. Alright, so that will create a slider with those presets. It'll be set to integer values, no decimals. Now we can connect that, move it up 20, copy, paste, and I'll set this one to 10. All right. Everybody have their curves moved up? Anybody not? Okay. So we're going to create a loft. This is where, again, the order matters. You have to go from one to the other. Going to go to the Surface tab. The freeform surface has most of what we'll be using today, but loft, create a lofted surface through a set of curves. First curve either is the top or the bottom. Drag it to the loft, to the curve input. Now, to do the other ones, you have to hold Shift so that they can connect. I'm going to go ahead and make mine a little bit taller. To modify the slider, you just double click and it gives you all the parameters. So I'm going to push up my range to 30. You guys can set whatever looks nice to you. There we go. And you'll notice that this is not rendering very well. Got the segmented connection. The surface is actually being calculated perfectly. It's just that the display is rendering it quickly, so it's got kind of rough, jagged edges on. If you were to bake this, you don't have to do this one, but the baked surface is goes all the way straight to the boundaries that we defined. So the actual geometry is nice and smooth. Alright, so the exercise that we looked at showed kind of how did we want to take this shape, this amorphous shape, and rationalize the panel system that would cover the surface. So the direction that I'm going to take for tonight is we'll start with the idea that we'll have a kind of a rational horizontal repeated structural element. So I'm going to do the intersects with this and create the contour lines, create horizontal contour lines at a set spacing, and that'll be kind of the start point for our grid that we're going to apply to this. Now, the command that we're looking for, so back here at the back, there's intersects and transforms. Intersects have all of the topological operations that involve intersecting, splitting, all of that stuff. That's the events and the Boolean operations that are the combinations of two different types of elements. So in this case, we have a surface, which is also called a B-rep, or B-rep is a type of surface. So we're looking for, I think this is the one I want to use, a brep and a plane. Yep. So that one's not the easiest to find with just the plain old search, because they're just intersect doesn't pull up exactly what you want. You have to be very specific when you find the name and the type, and so there's a whole slew of different ones that are different types of geometry and different types of topology running into each other. So there isn't kind of a catch-all. It's one nice thing in some of this choice gets obscured from you in CATIA or in Digital Project. You just have one kind of mass intersects command, and then it does the decision for you depending on what you bring into it. But here we know we have the surface, and we're going to create the planes now. So there's a couple ways to do it. I'll show you the most explicit first, and then some of the tools that it has built in to help you. So if you go to vector, vector again has the planes, points, and vectors. So the very primitive geometry. And we're going to do XY plane. That's what we drew our curves on, so that'll be parallel to our surface. So you can do mouse over the O, and this one just by default is defined at 0, 0, 0. Now, there's a couple different ways you can push a series of points into this and make that if you pushed a bunch of points at different elevations in, the resulting would be a series of planes. You can also take this and you can move this one a certain number of times. They both are valid. I'm going to do the moving, a little less work. So we're going to grab the same move, use the same box. You can just copy it here, paste it. I'm going to go from the plane result of the XY plane component into the geometry input. Now you can see, because it's still, mine is still moving it to the top, so it's moved it 30 units. I'm going to right click and disconnect this one because I'm going to use a different series here. So to disconnect, you go right click on that, and disconnect is a choice, and you can do that. Sometimes you need to do that, like on this where the curve has multiple inputs, the disconnect gives you the individual choice if you had to reroute a couple different things. So you can remove one curve at a time. Alright, so now we have our move, we have this empty vector, and here's where we're going to have to feed it a series, because we want to move, for today, let's say that mine, I'm going to do a 2-foot horizontal grid. So I want to make a series of numbers that go from 0 to the height. I move mine up to 30 and have a spacing of 2. Under sets, there's a whole bunch of operations that help you make these series and do them parametrically. So this one, I can lock it into my 30 and it will follow that. So we're going to do series. Okay, it's a not sequence series. Create a series of numbers. So the series that we're going to create is the height, the different heights we're going to move that plane. You look at the input start, step size, and number of values in the series. Right now we can just explicitly, we can type these in. So I can 0, I'll leave. I could set this at 2. Right click, it says set number. And 30, so 2 times 15. And that gives me a series of numbers there. But if I change this, then that's going to invalidate this one. So let's wire them up together. And actually, I even did the math wrong. It's actually stopping at 28, which is short of the top. So let's just wire this up parametrically with this one so that when we change the height, it will change the number. So there's two things we have to do here. We have to figure out how many, and we have to figure out what the spacing, if we want to leave it 2 or if we want to make it flexible. So I'm going to go ahead and copy one of these again, put a slider down here, and I'm going to double click and set my range for the spacing. Let's say, for me, I'm going to set it at 0.5, maximum of 4, and this time I want rounding. This changes it. If you click N, you never have any decimals. R, then you have a rounded number, so you can set the number of decimals. I'm going to just leave it like that. So 1 decimal point, minimum 0.5, max 4. For now, I'm going to set it at 2. Okay, so to get to the top, we said I needed 16. So I think the math, because I'm dividing by 2, so if the height's 30 divided by 2 is 15 spaces and 16 divisions, because you get to count 0 and the top. So the math I think we have to do is take this divided by that plus 1. So let's start with math and grab the divide. Drag the 30, drag the 2. Okay, so I have 15. And I'm going to go ahead and just drag that there, and I'll do the addition within here, because it will, you could do it within the plus box, but this is the other method as well. So right now it's giving me, let's check. So if I mouse over, I'm getting 0 down to 28. I need one more step. So the way you, on the fly, add that change, right click, and under expression you can modify this. So it cares about the name, so this is the number coming in, this is C. So I say C plus 1. So this takes whatever value was coming into C, does something to it. If you were to do the same thing here, you would take, and it would have to be S. So it's always the name of the variable, the name of the input. And you said, when you did this? Interesting. All right, well, the other way to do it that won't cause an unknown variable, if yours isn't working, is just add a plus. So you take the output from here, we're going to add 1, so right click on the second value and set the data to 1, and then reroute that up there. Does that work better? So when all said and what's that? Yeah, you have to go and if you do want to change it, you have to come back in here and delete all the expression. I don't think it works, but maybe it does. Didn't used to. No, it just sets it at 1 then. Okay, so everybody should have 0 for the start point, whatever your value is, and then some math behind getting to this. And you might have some weird scenarios, since if you had set it at 29, I'm going to get some weird rounding, but because this So even though I have 15.5 coming in, it's going to pop it to 16. So I'm going to leave this for now for even. You can even set a slider to let you do that, just to keep it nice and happy. So I could set that to only even values. Now I'd always have that. All right. So we did all that just to have these numbers, this list of numbers, 0 to 30. Each one of those is the distance we want that plane to move, and that's where our cut will be. And that's the distance we want this to move in the z direction. So we're going to go back to our vector that we had here. That's under vector, vector zone, and then unit z. When I pull these values in, so by default it's set to 1, I pull it in, now I have a translation vector of all of those values. Because move won't work just by giving it distance, you have to give it distance and direction, and that's the kind of the definition of a vector. So we'll go ahead and drag that there, and now I should have all my planes at the spacing. And we should have that flexibility here to increase or decrease. And again, I'm kind of, because I'm pushing a decimal in here, I might get some weird out of bounds results. Yeah, but that's okay. Once you have your loft and your planes, now you can create the contours. And if you look at we left this over here before, the B-rep plane intersect solution. B-rep essentially means surface, so that you can pull from there. And then G is the translated geometry, which in this case was a plane, so we'll pull that out. And now I have my contours. So now when I modify this, I can affect the density. And you'll see it's a little bit, you're seeing some of the definition curves in here as well. If you want to hide those, you can always group select anything. So I'm going to go ahead and group select this whole group here, right click and preview off. I also don't need to see these planes, so we can hide the move. Now you should also be able to do this. This is breakable, but you should be able to change the height and the shape definition and have your contours follow along happily. All right, does everybody have the contours? Anybody not? Okay. All right. Now, most of the time when in my experience, when I've dealt with patterning, there's kind of two ways that you deal with rationalizing curvature in architecture. And the first way is you deal with ruled surfaces. And ruled surfaces means that it is something that can be created basically out of a piece of paper. A cone or a cylinder, or in reality, in a lot of architecture, kind of a series of combined partial cones and cylinders make a surface that as an architect you can, in the computer, flatten that surface, work in the two-dimensional arena and add a pattern, and then roll it back up onto the building. And a lot of even, a majority of Frank Gehry's surfaces that look pretty complex, highly dual curve, are actually all ruled surfaces. It was a requirement of the material that they were using to clad the surface, that they weren't able to deform in 2 dimensions. They're always only able to kind of deform in 1 dimension, mostly, slightly in 2 dimensions. So they always did a lot of work to create surfaces that were ruled. This surface right here that we just created is not a ruled surface. You can't unfold that because of the way that I made the individual curves that we defined it by. So in order to pattern this, you have to start in the 3D. You can't flatten it. Even if you did flatten it, there are approaches that let you flatten it, and they approximate a flat, kind of the same way that a map approximates the flat of the Earth's surface. All of those start to put varying degrees of error into it, so that when you bring it back together, it's not going to actually come together correctly. When you say, okay, I need to put this skin here, it won't fit because it's been designed to a surface that isn't exactly the 3D reality. So the next phase is that you start to deal with the patterning in 3D, and that hasn't been a whole lot of work in that space until recently, because there's a lot of computation behind it, and then there's also a lot of unique fabrication to it. And if you spend the time, and then the third is you could also spend the time to really create a sort of custom lattice that would have similar families of components, but that's also been very challenging in order to develop. So we're going to do kind of a combination tonight. We're going to do the pattern in place, and we'll lay it out with some rules, and then we'll take a look and evaluate how the surface is, and then pass it back through. So the kind of simple way that I'm thinking, okay, if I had to build this, I could create these cut lines, I could fabricate that shape. If I was going to use the laser cutter, I could figure out all those curved contours. I could cut out that profile, and then I could mount those to something in my, whatever my 20-foot unit is. If it's 20 feet, I could mount them at 2 foot on center on a central pole, and that's my shape. And so my skin that I'm going to define to my unitized, or my discrete skin that I'm going to use to define that surface, you can come back and do pieces of fabric and start to attach to it, but we're going to do a segmented or a small component. So I'm going to start by doing points along that curve. That's a starting point for, yes, I'm going to have individual points along that perimeter that I'm going to attach something. So we'll go ahead and we're going to start to do some analysis on the curve. So under the curve tab, division, you have a couple things here. We'll do divide by length. We used this in the time before. This is so it's a curve, and then it gives a starting just value for how far that is. So for now, let's start, and let's just set this. I have 2 foot spacing. Let's set it at a 2 foot. Division. All right, so let's look at the data that came out of this. I'm going to go ahead and simplify. Simplify just removes all those leading zeros when we look at that. And this is now tree structured data. It's structured data. In the curly braces, you have 0 through 15. Those represent the individual curves. The N represents how many points are on each curve. And our curves are all of different lengths. So we have values ranging from 28 to 34 of what I can see here on the screen. Depending on your curvature, you'll have different number of points. And we're going to go ahead and leave this structured. If you remember, flattening and grafting was what we started to introduce last time. If I flatten this data, you can see that all of that structure goes away, and now I still have all the same number of points. They just are in one giant pile. But We care about dealing with each row individually now, so we're going to leave that. So I'm going to leave it unflattened. We'll leave it structured, but that's what's in there is just a series of points. Now, in order to put something on the surface, the thing I need to know about it in order to give it orientation is really only what would be the normal vector. So normal vector is the direction pointing directly straight 90 degrees off the surface. So, you know, if you have a perfect cylinder, the normal vector is always something pointing away from the center of the cylinder. So in this sort of amorphous loft we have, it's going to be very similar. It's going to be something pointing straight out, but you can imagine if you had your right angle finder, you set that on the surface, and everywhere it's going to be where it would point straight out. So we need to evaluate the surface. There's a couple tools also now under surface that we'll use to do that. So the first one, if I can remember the right name, I think that's it. So evaluate surface seems like the right answer, and it actually does have the output of the point, the normal, and the frame. Now frame is a plane. That's the name of a plane that the Grasshopper writer gave it. Normal is a vector. That's what we were just talking about. But all of these have this UV after it. And the concept of UV is just a local coordinate system for every surface. Kind of the way it does its own internal tracking of the topology is it gives all these surfaces this sort of pseudo coordinate system. And it's not something that is units. It's independent of units. So in this case, what it's asking for is a surface and a UV coordinate. All our coordinates are in normal space. We have x, y, z's. UV would be that point on the surface, the UV point. So there is another component that you use to find out what the UV value of your point is in 3D space. So you want to do point closest. I think this one's it, yeah. Or no, we can just do this one. Surface closest point. Everybody have that one? All right, it has just two inputs. It has point and surface. So over here is our loft. We'll pull that forward as the surface. And the structured data of points, that's the points we're going to pull forward here. So you notice there's no change to the preview. All of this is the same data. It has closest points. Our points were already generated right approximately to the surface. It would have projected them if they weren't, but so we have the same set of points. But we do have now our UV coordinates, which is the equivalent coordinate on that surface for all those individual points. So in terms of the way these match up now, pull the loft forward for the surface here, and our UV coordinates, which you can see have the same data set. That data set just keeps following through. We have our 0 through 15 and all the individual coordinates. All right, now it gets a little crazy. So now what we're seeing here is all of those solutions that we looked at before. So this is points, normals. Normals don't show up in the display in the preview, but we have the frames, and the frame's the plane. So what you're actually seeing here is all the planes overlapping on top of each other. So all of this is just for information. We can go ahead and hide these two. We'll just use the data. We don't need to visualize it. All right, so this gives us enough information just to start our first rough pass at the geometry. So we'll come to curve, and we'll do a couple of them. I'm still dealing with primitives. we'll get to a little more complex shape, as Jared asked about 2 times ago, but I'm going to do a circle. So you can double click and search for it, or go to the primitives under curve. I'm going to go ahead and do polygon. And rectangle. Okay, for all of these, they're basically the same in terms of input data. For the points are the ones we solved here. You drag them forward. And there's our solution of circles. By default, it's saying they're all on the XY plane. Now the frames are the planes that are, oh, sorry. So actually, yeah, so the frames is what we actually want to pull forward. So the frame is a plane and an origin point. So it will pull forward that data. There we go. So that gives us our orientation and location. So all those should be parallel locally to the surface. And now radius we have set at 1. Kind of works. I'm going to hide some of these points. Can hide everything up until the oops, leave the loft, but I want to hide anything that has that central point. Okay. Things are okay, pretty tight here. Actually doesn't look too bad. Let me actually go back and adjust my starting curves, because they're a little too simple. Where'd they go? So I'm just going to go ahead and spread out mine. Where'd it go? Super weird. Or maybe not. Oh. I always do this. There we go. So, because these are back in the Rhino world, not parametric, I have to adjust them manually. This is a control point curve. Even with the gumball on, I can't get to the control points that defined it. Under curve tools, we messed with this in the previous session, there is a points on, points off that turns on and gives you access to the data. So I'm going to make this guy a little bit bigger on the base, give a little more diversity to my surface. So what you'll notice is in this area here where I'm most like a cylinder, then I have pretty good distribution of this data, pretty good distribution of the points of the circles. Where I have a little more complexity to the surface, it's starting to pull apart a little bit. So at the top of the bottom where I have a little bit more shape, not everything's connecting as nicely. If I even exaggerate this one even further, where does it go?
Then you gotta hit escape.
Ah, thank you. Again, I don't know Rhino very well, just Grasshopper. Come on, there we go. All right, I turn back on, I'll have even more kind of split. Okay. So let's finish wiring this up really quick. Radius 1. Go ahead and make our hexagons. So radius, we'll set this one to 1. And you can wire the same thing here. So points, and I'm going to go ahead and leave it. It's already set to the default on the 1 direction, but I'm going to change the Y, set domain, -1 and 1. If you want to make it look even more like chiclets, you can add a radius to the corner. Yeah, the Y by default comes in as -2 to 2, so I set it back to 1. But we'll come back. Right now those are non-parametric because if we changed our grid size, this would all stop looking so nice because, so I'm going to leave polygon and rectangle for now, turn back on circle. So we say the radius is 1, which kind of nicely matches our spacing of 2. If I were to increase this now, I start to really fall away from it. So the evaluation piece here is we're going to take a look at what size would make sense for these. Because these ones actually need to be taller in order to fill in the entire row. But that means if you can't just make them taller, they'll overlap. So we also have to change the spacing that they are going around the curvature. So that's where we're going to start to do is figure out how do we evaluate what they should be, and then figure out how to send that information back to the beginning and reset the spacing. Because all of these by default we said, okay, a good starting value is just divide by a 2-foot spacing. So first half of that is the evaluation, is how do I decide what this should be? And right now, if I were to look at just this individual one, which is kind of hard to see because they're all, the ones that it matters to really is okay, the ones next to it, but also the ones next to it on the next row. But I don't, this one right here, circle 2700, doesn't care about this one. It's too far away. So there is a tool that will let you do sort of this kind of evaluation, and it's under the meshing tool, because a lot of these concepts that we're talking about are also used to build and rationalize faceted surfaces. So proximity 3D is one that will give you the closest compadres in a set of data. So that's under mesh, triangulation, proximity 3D. If you look at the inputs, it says input points, maximum number of closest points defined, search radius. All of these are optional. I think we'll just stick with our 5. If we look at our circles, that's, let's count. Let's go 1, 2, 3, 4, 5, 6, 7, 8. 8's about the maximum we'd need to know. And we'll play with that. That may or may not be the right value when we start to evaluate and see what the results are. So the points now that we're going to feed into this come all the way back here. They're straight out of the divide. Now, here's where we start to come back to our data structures. Because what this did is it evaluated the points within the structured data. So it said, okay, you have all these 15 rows. Let me just look at row by row. Well, that didn't really work for us because the data that we care about is actually outside of the rows. We want row 1 to look at row 2 and to look at row 0. So in order for this to evaluate it correctly, we need to flatten the data and give it everything. So I'm going to go ahead and say flatten, gives it all 497 points. And now my data is going to look, so it's going to take every single point and tell me my 8 closest points out of that set in 3 dimensions. So the result is back to structured data, but it's something that sort of makes sense for what we needed to do. I have that leading 0. I'm going to go ahead and simplify so we can take a look at this. So now our inputs were 497 points. So we have 497 rows here. That's the curly braces. And for each one we've solved, and we said there are 8 solutions, 8 numbers. Now, let's grab the panel, and panel is back under parameters. Remember this guy with the yellow? This helps us take a look and see what's going on when we have structured data. Okay, so mouse over, okay, so it says proximity links. That's really, I don't know what that means. What is a proximity link? If you look at the panel now, you can see, okay, what it's actually giving me is lines. And if you click on it, you'll see now that's what it's building. It's building this grid of points. And for our purposes, we care about distance. So even though it gave us this geometry, we'll go ahead and right away convert all those lines into a length. So curve, tab, analysis, you can grab length. You can double click and grab length. It's just measure the length of a curve. So the data is structured the same. I still have 496 individual points and then 8 lengths associated with that. I can drag that over, and now I have all these. And there is no order to it. Oh yes, there is. Okay. So it automatically sorted length. If I look through these, every single solution, it was very nice and did the evaluation of what was the closest and what was the furthest away. And what we care about isn't what was the furthest away, we care about what was the nearest one, because that's going to be the one that is the largest that we can make our circle and not intersect with an adjacent circle. If I made, so in this example, 2.0 here, that makes sense. That's probably in the center of our solution, and it should be approximately 2 inches. The furthest one, if I made it 3, it would expand out all over top of all of those other solutions. So the one we care about is the first one. Now, how do we get to that? Because we have this sort of weird structure. Sets is the tool that lets you manipulate lists of all sorts. So what we're going to do is we're going to select the shortest or the first item out of all of those 498 solutions. And so the box you'll be looking for, there's a whole bunch in here that tell you about different abilities to manipulate lists, but we just want to grab one item out of a list. So list item, if you're searching for it, or list item in the toolbar is the one. So if you look at it, so we're going to be passing lists, and it says, okay, what's the index of the item? And in terms of the way that the Grasshopper keeps track of this data, so we look over here, we have our curly braces are the branches. That's the individual points in this case. And then we have a solution. We have 8 solutions because we told it to give us our 8 closest points. The way it keeps track of those 8 is it numbers them from 0. It always starts with 0, which is sort of annoying, but it counts them from 0 to 1, 2, 3, 4. And since it already sorted the values, we know that the first one, item 0, is always going to be the shortest distance out of all of those solutions for each one. By default, it already comes in items as grabbing item 0. So if I go ahead and drag this list over here, just to show you what's happening, I'm going to create another copy of this panel, and we'll put it side by side, and we'll look at this here. I'm going to scroll them both up to the top. So if you look here on the right, this is your branch. This is the one of the solution points. And the first item in the list is 1.9, blah, 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 blah. The item selector grabbed that one item. And so now I have, instead of a list of 498 times 8, I have a list of just 497 points times 1. And now this is the size of that radius that will make sense for the row-to-row spacing. So we'll cover up this gap that we're building here. I'm going to leave those up just to grab them if you have any other things that you're looking at. I'm going to go ahead and hide the proximity. We don't need that matrix. I'm going to pull these a little further back. So one more piece of this is we can pull back and take a look at, okay, so now we have these 496 points, and, sorry, 497 points, and we have 497 circles. If I drag this right here, it's not going to be very happy. If you look, it's now making 19,700 circles. It sort of looks like it's right, but it's kind of all over the board. This isn't what we expected. And if you look at the reason is because the data doesn't come in matching. If you look back, as we flow through, we keep having this same nice structure. We have 16 branches, and a certain number of points on each row. When we flattened this, we lost that data structure. It went away. We gained a different one, which was each individual point. But now I'm kind of mixing streams. I have completely different data streams coming in, and it's saying, what do you want me to do? I have 15 times whatever here, and now I have 496. And so it's mixing it. So somewhere in the middle now, the solution is like 496 times 15. So it's trying to say, hey, I think I know what you want to do, but it's really not. There is one more thing. It's a little bit obscure, but what it will do is it will take equal length sets of data, and it will match their trees so that they can flow back together. So we can take this radius that we just solved for and push it back into the circle, and it matches up with the right point. There's something called, so we did flatten. That was the right click here, and we flatten. There's something called unflatten. That's a box. If you say unflatten tree, now the trick is it needs two things. So it needs data tree to unflatten, and then a guide to match. So any of these ones that we have up here would be able to be used as the guide, because they have the row by row data set that we initially started with. So I can go ahead and pull that down. You can pull it from the frame. You can pull it from the UV coordinates. You can pull it from the points. They all have the same data structure. And the problem is the result still isn't exactly right. What we want is 0 through 15. Oh, that did it right. Great. So because these were the same numbers, it went through and said, okay, you had this organized in this way of dividing things before, then you had this way of dividing it. I'm going to match the first way, and it is taking all those and putting them back in the right order. If at any point we had really mixed up the list, it would have matched it, but it wouldn't have come all back together. Everything we did, though, it kind of left them in order. Even though we said flatten it, it said, okay, well, this was my first row, and I put it 0 through this many, and then I put my second row. It didn't just throw them all into a big bucket. It took it apart in the order that was specific before. And there are some operations you can do which will sort them and move them around. But because we didn't do any of those, it could basically kind of take it back and match it together. So that result now is the same data structure. We can pull it up. And now we're starting to get better. The problem is now we're dealing with radiuses and diameters, so we need to do a divide by 2. So we'll pull that there, divide that by 2. Oops. And don't do that. Now we look at it, and what I notice is that it's still starting to sort. It looks identical to what we just did. And the reason is its data set is, we looked at that network. It was grabbing all of these, and we grabbed the closest one. The closest one was here. So in order to solve this, what we actually have to do is change that initial spacing so that it's much bigger, and then it will solve for the ones that are on the next row. So I'm going to go back here and just change the divide length, and I'm going to double it. So now the opposites happen. Now we're optimized from row to row, but our spacing around the curve is broken. And this is where you get stuck, because there's kind of no good solution. I can either have things that are better in one direction or better in the other. And so this is the part where you get to where people threw their hands up and they said, okay, fine, I'll just make a cone. Because I get in this loop where I'm good in one direction, I'm good in the other. but it never is kind of making this uniform pattern that's going to be contiguous across whatever the geometry is. And the thing that we need to do in order to do this is you have to create a feedback loop that is going to change the way that it's defined. Because right now we've solved for one good thing, which is the row height is correct, but now I need to modify the spacing. But some of these need to move closer together than others. You know, these don't have to actually move too much to be kind of touching and be closing that space. These ones have a lot further to go. So that's where the last part we'll talk about hoop snake and add that feedback loop, because hoop snake's designed to do this sort of iterative and analysis, and there's a lot of different ways you can use it. Today we're going to use it to make the spacing adjust, and so we can get adjustable spacing both along our rows and also in the individual skin's height. Here, you don't have to follow this example. This is an example you can download, and I'll send to you after class. It comes with the, let me go ahead and save so I don't lose this. So this is the example that he always sends out. It's a genetic tree develop, so hoop snake's tree. So basically, he's just built geometry to say, start with one curve, randomly pick two angles to divide that by, and start again. But then the trick is to loop that, to keep going, to say, okay, once you've done, now I have two branches, we'll do this again for each branch, and again and again. So the hoop snake, what it lets you do is it lets you step through and say, repeat that step again. So here you start to get sort of pseudo-natural looking component that's based on this iterative process.
The example of a recursive process.
Yep. And it's an old definition. I'll send it. It still works really well. And you can go ahead and play with how much flexibility you give the tree parameters and rerun it again. If you run it a second time, it will still follow the same path unless you change the seed value. But it will give you sort of a natural sort of rule-based evolutionary way of modeling. We don't have that many steps required. We have a much simpler problem set. But we're going to use HoopSnake to give that feedback. All right, so I'm going to go ahead and switch back to my solution here. Okay, so the place where we need to have additional flexibility is the spacing around. That's pretty much anywhere you're typing in a number. That's probably where you're going to have to do something. That's where we're always going and putting a slider or putting something to parametrically evaluate. I mean, at the moment, you can even also play with this and see how changing things like the spacing and the heights will affect it. But this was one where we said every row we're going to start with a four unit spacing, and that's where we need to do the feedback. And this is a case where it matched. So I have a data structure here with 16 individual rows, and it said, okay, for each one of them we'll use the 4. But now we need to do a different number for each. And so the first thing we need to do is make that data big enough so it's got a unique value for each one. We're going to start with 4, but we need to have, it's kind of silly, we have to make 16 values of 4, duplicate values of 4. So there is a, because you have to do this often, there is a duplicate data component. And it's pretty simple. It just says empty data to duplicate. We'll go ahead and just give it a number. We'll say that is our 4. That's what we're going to start with. Numbers of duplicates. That should be same guy here. We need the same number of results. So I'm just going to pull it up. And the O is list order, I don't know, that doesn't matter. So this way we've connected it with our parametric quantity of rows. And now if you look at the result, it's just the number 4 16 times. And so I can pull that right up here, and it acts exactly the same. Whoops, graphed. No, it doesn't. So we need it to act like it has the same data structure. So graphed, there. So now when you look, I have 15 branches of data. I'll simplify that one too. Okay. 15 branches of data. And so there's a couple ways we can look at how to figure out what should be that next number, because the base of my shape is wider, has a larger radius along those curves than the top, and the middle is much smaller than both. And so what I care about, I'm going to just start as an approximation and say, okay, let's take that new measurement of this curve, this new measurement of all these circles, and they mostly look the same size. They're not all exactly the same size. But if I just average all of those, that can be my new spacing. That's a good starting point for an approximation. So if I come back here, where did we get that data? This is what we were using for the radius. What I'm going to use is there's an average. Under math. I think it's under utilities. Yeah. Average for a set of items. We want this to be the radius? No, the diameter. Well, we'll try both. I think it's supposed to be the diameter though. Yeah, diameter would be center to center, correct. Okay, so this was our diameter. We divided by 2 to get to the radius. So I'm going to pull this guy in here. And what this is doing, again, a lot of today is about how things are doing things within these different data structures. So T had 15 or 16 branches, varying degrees, varying numbers of items in those lists. The average is going to take those in and give you the average for each branch. So you have a result of one value. And now I have a bunch of different data. It starts wider at the base. In the center of my data set, it's closer to 2. And then it gets wider again at the top. I'm going to go ahead and delete these just so we don't have wires going around everywhere. Everybody have and find the average. And here's where I say, okay, well that's what I want to feed back in over here, but I already am feeding something in there. So I can't just, we can try it, but it's probably wrong data structure anyway. But I already started with something. If I change it again, it will create this loop, I'm not going to actually be able to get the result I want. Because it's not going to say changing, since there was something that already created this average, if I feed back in the average will be recalculated, and you can't do something that loops back onto itself. Within normal Grasshopper, that's what the hoop snake will let you do. So we'll go ahead and grab this guy. And it's got a bunch of stuff, but we only need a very small piece of it. Everybody remember hoop snakes under extra, and then whatever VOLA stands for. But on the input side, you have starting data. This is the output before any of the looping has been set. So for us, that's this value. We said, let's start with 4 as our spacing for each row. So I'm going to go ahead and drag that set to there. Now, that is the data that it has. I think I have this right. Let me make sure. Yep. Now, it used to be more descriptive. This, where it's saying represents a collection of generic data. This is going to be where I'm going to replace that starting set. So I say my initial definition is for the next one's going to be the average coming out. So here's where I can actually do that sort of looping. So I'm going to grab the average output and pull it back to here. Okay, feedback output. And here's where it explains what the difference of D and S are. So you get a copy of the data D, or S if there is no looping already going on. So now we can pull this up here. Now the one thing we have to look is make sure that everything's coming in the same way. So this is structured. I think I'm going to need to flatten this. I'll try that. Okay. So what the hoop snake is going to do now is, just because it hasn't run yet, it's going to just pass the first default value. I'm going to right click, and you can either double click on it and it'll bring up a dialog here. It's probably the easiest. Right click gives you about 1 million solutions and items that you need, but for the most part we're just going to deal with the few that are defined when you double click. So first thing is just reset all. Everything will turn orange for a second and it'll reset. And now the play button is going to step 1 time. And what it did is it said, okay, I ran it once. I got this output that you calculated some values on your first solution. I'm going to pass that back through. And then we can run it again. It's not perfect, but you can keep hitting it and you'll notice it get some slight changes as we go, where it's getting slightly tighter, slightly tighter. Because of our assumptions, we're never going to get there with this bottom row, because if you look, I'm tight over here, I'm tight over here, but I'm separated here. The assumption we made is we would say, okay, the spacing along the whole row is going to be the same. That was the average. By averaging the average size of all those skins, it was going to give us the same distance for each one. But so you'd have to take it even a little bit further, a little more three-dimensional if you wanted it to keep iterating and moving everything perfectly together. But you might also have to let go of then also staying right on your horizontal guidelines. So this is just a nice, quick way to try to get close to a solution that is going to pack all the circles onto that surface in a way that we can hopefully build and kind of specify. And it should work if you, now that you've kind of solved this solution for the radius, the position, and the quantity, you can come back up here and take a look at some of these other ones. So we'll have to pull the R. So the R was this guy. We're going to pull it up to the polygon. and you can look at look at those. Why is it? Need to turn up my settings on the output because it's doing lightweight. There we go. So it works good for that. And then also here we got to do a little bit of work because we need, if you want to, I'll do it quickly, we need to make a domain. If you remember from before, those guys live under math. Construct domain. I'll set this at negative A. All right. Whoops, way too big. So radius. There we go. Now we have our kind of chiclet packing, works the same. There's a lot of different examples of what people use HoopSnake for. The biggest way that I think about it is Grasshopper likes to think about things as like one solution. I start at one end of the chalkboard and I go to the other end. And it's, you know, some people, when you're on Grasshopper, they'll talk about it in terms of it's deterministic. I start with these points and then I have some geometry at the end once I do all of these manipulations. Ours, we had this point where we had information in the middle that should go back to the beginning and change how we did it. And so HoopSnake lets you do that recursive sort of logic where you say, okay, I start, I do some work to figure out one thing that I need to feed back to the beginning. It's not the normal way Grasshopper deals with it, but there are a couple different ways that it's designed to do some of these recursive algorithms that start to pop up when you have more complex solutions in architecture. Any questions on this part, or anybody get stuck or have some comments on this?
So, like you were saying that Frank Gary's office is doing this, they just ended up not working with them on paper folding because, so like, do you guys do, I remember what the two types you're talking about, but do you guys do a lot of work with this kind of HoopSnake stuff, or it's not a single piece of paper?
It's just starting to. I mean, the tools, you know, having it be this easy, and Grasshopper didn't exist just a few years ago. So you had to have like a computer scientist come in and help you make a program that would be able to do recursive computation. There is a capability to do it also in Digital Project. I think it just was a hard problem. I mean, this looks a lot like a project you guys probably are familiar with in Mexico City. There's a museum that looks just like that shape, and they rationalize the surface for these white tiles. And that project was all done with Digital Project and a little bit of extra juice on top of it. But so I think it's just that now it's becoming both an option in terms of easy calculations. Like, you know, this is an hour and a half of tutorial, but if you look, I mean, we have a very small percentage of components here. And so there's some others that I've gotten from firms where they're doing surface patterning, trying to create sort of mosaic tile imagery, really varying sizes and quantities and colors in a very like I would say specifiable way. Like they say, here's the design. It's a completely crazy surface, but I know I have this many of this size, I have this many of this color, because they did all of the computational work to do it. So I think people are starting to approach this where it was kind of computationally prohibitive before, and fabrication, like both getting the computation to figure out just the geometry and then trying to communicate that to a fabricator to say, okay, you need these, 600 of this shape and 700 of this shape, and they go in these positions. So
how did they make that shape? What machines do you use?
well, like in this case, we just made a flat shape. Like, so this is an approximation of the surface. We didn't say on ours that we would go and we would mill out that to the perfect thing. We discretized it down to an easily fabricatable component, and then you could do the same. So the examples that we looked at in the beginning, there's a lot that do that same process. The Zaha project, the Andrew Monto's installation, and the last one we looked at, I don't know that artist's name, but they're all about kind of breaking it down into something that's easily fabricated with the sort of two-dimensional tooling tools we have, because real 3D shapes are still very expensive. They're 5-axis milling, lots of waste, or they're additive manufacturing with lots of wait time. And any other questions and comments? So just a reminder, quick, small assignment that we talked about last time. Everybody has to take some piece of what we did so far in class and extend it in some way, combine it with another one. Just the goal is to start to familiarize yourself with the tools. You can do CATIA, take an example we did before, or Grasshopper, open it back up, extend it, add some additional component or design to it, and email it to us. I think you guys said Friday was the preference. So that's what we're planning on. For the time after, we'll do the review of everybody's study, kind of project study, talk about the different cases, and start to make some strategies for how we might do the project. And then in terms of, I think we will know at that point in terms of how big the groups are, but the goal will be to split this group into a certain number of work groups and pair it with some people from the other course, and we'll start the sort of design charrette 2 weeks after spring break. Any other questions about the assignments? Or
would you email us outline of the research?
Yeah, I'll send out just a little blurb about the a reminder about the exercise for this week, and then I think Jonathan, could you send out just a quick explanation of what we talked about? Just the yeah. And I'll send out the links. I mean, there was lots of good examples in those 4. So. All right. Thank you guys very much.